Right now, at this exact moment, somewhere on Earth a volcano is erupting. Not metaphorically, not historically. Right now, tonight, as you lie here, molten rock is breaking through the surface of this planet and flowing toward the sea. It has never stopped, not once in 4.5 billion years. And tonight, we are going inside it. Hello there and welcome to the Sleepy Science Facts channel. Tonight, we will be drifting into the world of volcanoes. Not simply the dramatic images of lava flowing into the ocean or as clouds rising above a distant peak, but the whole of it, the full, ancient, and deeply extraordinary science of the most powerful geological force that shapes the surface of our planet. Volcanoes built the ground you are lying on tonight. They created the atmosphere you are breathing. They produced the water in the oceans. They have destroyed civilizations and just as quietly made new ones possible. They have triggered mass extinctions and in the same geological breath cleared the ecological stage for entirely new forms of life to emerge and flourish. They exist on every planet in the inner solar system and on moons of Jupiter and Saturn so cold that they erupt with water and ice rather than molten rock. They are active in the deep ocean at depths where the pressure is so extreme that the lava cannot explode but instead oozes out in smooth pillow shapes onto the ocean floor, building the mountain chains that represent the longest continuous geological feature on Earth. They have been the subject of human fear and reverence for as long as humans have lived near them, and the science behind them has been accumulating for centuries without the mystery ever quite running out. From the supervolcano sleeping beneath Yellowstone National Park to the permanent lava lake that has been active in Ethiopia for as long as anyone has recorded, volcanoes reward attention with something genuinely extraordinary at every scale and in every corner of the planet. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften and allow your breathing to slow and allow the day to gently fade away as we explore the mysteries of volcanoes together. Let's begin. A volcano is a window into the interior of the Earth, and what it reveals when it opens is a product of conditions so extreme that the rock itself has become liquid. The interior of the Earth is hot for reasons that go back to the very formation of the planet. When the Earth accreted from the material of the early solar system approximately 4.5 billion years ago, the energy of countless collisions between planetesimals heated the young planet to the point of being entirely molten. As the planet cooled, heavier elements like iron and nickel sank to the core while lighter rock rose to form the mantle and crust. But the cooling was not complete and has never been complete. The Earth still holds an enormous reservoir of heat from those ancient collisions, supplemented continuously by the heat generated by the decay of radioactive elements distributed through the mantle and crust. This heat has to go somewhere. It moves upward to a rock of the mantle by convection, in slow currents of solid but plastic rock that rise from the deep interior and sink again as they cool, in cycles measured in millions of years. Where these convection currents bring hot mantle material close to the surface, or where tectonic plates pull apart and allow the pressure on the underlying rock to drop, the rock melts and becomes magma. Magma is less dense than the surrounding solid rock, and this density difference drives it upward through cracks and weaknesses in the crust. When it reaches the surface, it is called lava, and the structure through which it emerges is a volcano. The volcano is not an anomaly. It is the Earth's thermal exhaust system, the mechanism by which the planet releases a heat that has been building inside it since the beginning. The Ring of Fire is the most volcanically active region on Earth, and its existence is a direct expression of the geometry of tectonic plate boundaries around the Pacific Ocean. The Ring of Fire is a horseshoe-shaped zone of volcanic arcs and oceanic trenches that encircles almost the entire Pacific Ocean, running from the southern tip of South America up along the western coast of the Americas, across Alaska and the Aleutian Islands, down through Japan and the Philippines, Indonesia, Papua New Guinea, and New Zealand. It contains approximately 75% of all the active and dormant volcanoes on Earth and is responsible for approximately 90% of the world's earthquakes. The volcanoes of the Ring of Fire are predominantly stratovolcanoes, built by the subduction of dense oceanic plates beneath lighter continental plates, a process that drives water and other volatile compounds from the subducted plate into the overlying mantle wedge, lowering the melting point of the rock and producing magma that rises through the crust to feed the volcanoes above. The presence of water in this magma is critical. It makes the magma more viscous and more prone to trapping dissolved gases, and when this gas-rich, high-viscosity magma reaches the surface, the pressure difference can cause explosive eruptions of extraordinary violence. The volcanoes of the Ring of Fire are not simply geological features. They are the visible surface expression of a process that recycles the material of the ocean floor back into the mantle in a cycle that has been operating for hundreds of millions of years, building the continental margins that define the edges of the continents we live on. Let your breathing slow. There is no hurry here. The volcano we are visiting tonight has been building for millions of years, and it can wait for you to settle. The eruption of Mount Tambora in Indonesia in April of 1815 was the largest volcanic eruption in recorded human history, and its effects on the global climate produced consequences that reshaped the human world for years afterward. Tambora ejected an estimated 160 cubic kilometers of material into the atmosphere, producing a column of ash and gas that reached into the stratosphere. The fine particles and sulfur dioxide injected into the stratosphere formed a layer of reflective aerosol that circled the globe and reduced the amount of solar radiation reaching the surface. The following year, 1816, became known as a year without a summer. Average temperatures across the northern hemisphere dropped by approximately half a degree Celsius, which sounds small but was sufficient to cause widespread crop failures. In New England, frost killed crops in June and July. In Europe, the grain harvest failed across the continent, producing famine conditions that contributed to bread riots in France and starvation in Ireland. In China, abnormal monsoon patterns flooded rice fields and caused a Yunnan famine. Tens of thousands of people died directly from the eruption, and an estimated 70 to 80,000 from the subsequent famine and disease. The atmospheric effect of Tambora have also been cited as a possible contributor to the cholera pandemic that began in Bengal in 1817, as disrupted weather patterns and flooding may have created conditions favorable for the spread of the disease. A single volcanic eruption on an island in the Indonesian archipelago changed the weather of the entire planet for over a year, killed crops on multiple continents, and may have contributed to a pandemic that killed millions of people. Mauna in Hawaii is the largest volcano on Earth by volume, and it is one of the most studied geological structures in the world because of what it can tell us about the behavior of the deep mantle. Mauna is a shield volcano, a type built by the repeated eruption of low-viscosity basaltic lava that flows easily and spreads over large areas before solidifying, producing the broad, gently sloping profile that gives this type of volcano its name. Its total volume above the ocean floor is estimated at approximately 80,000 cubic kilometers, and it rises from the ocean floor to its summit at an elevation of about 4,200 meters above sea level, making it one of the tallest mountains on Earth in total height from base to peak. Mauna Loa and its neighbor Kilauea sit above a hotspot, a region of the mantle where an unusually hot plume of material rises from deep within the Earth and melts through the overlying plate regardless of where the plate boundaries lie. As the Pacific Plate moves northwestward over the stationary hotspot, it carries the volcanoes it has built away from the heat source, and new volcanoes are built in their place. The chain of islands and seamounts stretching from Hawaii to the northwest across the Pacific marks the track of the Pacific Plate over this hotspot, with the oldest, most eroded islands at the far end of the chain and the youngest, most active volcanoes at the southeastern end where the plate is currently over the hotspot. The Hawaiian Islands are not simply beautiful islands. They are a geological timeline written in rock, recording the movement of a tectonic plate across a fixed heat source over 70 million years of geological history. Beneath Yellowstone National Park in Wyoming lies one of the largest active volcanic systems in the world, and the landscape of geysers, hot springs, and fumaroles at the surface is a visible expression of a magma chamber that has produced three of the most powerful eruptions in the geological record of North America. The Yellowstone hotspot, like the Hawaiian hotspot, is a region where a deep mantle plume delivers heat to the overlying crust, but unlike Hawaii, Yellowstone sits beneath a continent rather than an ocean, and continental crust is thicker, less dense, and richer in silica than oceanic crust. When mantle-derived magma rises beneath continental crust, it melts the surrounding rock and produces a magma with much higher silica content, making it thicker, more viscous, and far more prone to catastrophic explosive eruption than the runny basaltic magma of Hawaii. The three major eruptions at Yellowstone, approximately 2.1 million years ago, 1.3 million years ago, and 640,000 years ago, were each supervolcanic events, eruptions of a scale and power that dwarfs anything in recorded human history. The most recent of these three eruptions ejected approximately 1,000 cubic kilometers of material, compared to the roughly 160 cubic kilometers ejected by Tambora in 1815. The crater, or caldera, produced by the most recent eruption, is roughly 70 by 45 kilometers across, and is a basin in which much of Yellowstone National Park sits today. Yellowstone is not overdue for an eruption, despite what popular media sometimes claims. The interval between eruptions is irregular and not predictable, but it is unambiguously an active volcanic system, currently producing one of the highest concentrations of geothermal features anywhere on Earth. Here is something that will change the way you think about the ground beneath you for the rest of your life. The lava erupting from different volcanoes can look almost identical on the surface, but differ from each other in chemistry and behavior in ways that determine whether an eruption is a gentle, walkable lava flow or an explosion of extraordinary violence. The key variable is silica content. Low silica basaltic magma, like the lava that erupts in Hawaii, is thin and fluid, flowing easily down slopes and producing relatively calm eruptions with spectacular lava fountains and slowly moving rivers of molten rock that allow people to observe them from relatively close range. High silica rhyolitic magma, like that in the Yellowstone system, is thick and sticky, trapping dissolved gases in a matrix that does not allow them to escape gradually. When this gas-rich, viscous magma approaches the surface and the pressure drops, the trapped gases cannot escape through the magma. Instead, they expand explosively, shattering the magma into tiny fragments and propelling them into the atmosphere in eruption columns that can reach altitudes of 40 kilometers or more. The difference in behavior between a Hawaiian lava flow and a Plinian eruption at a subduction zone volcano is fundamentally a difference in how much silica is in the magma, and therefore how viscous it is and how much gas it can trap. The same basic process, rock melting and rising to the surface, produces phenomena ranging from serene flow of glowing orange rock to an explosion that can alter global climate, depending almost entirely on the chemical composition of the magma involved. The eruption of Vesuvius in 79 AD and its preservation of the Roman cities of Pompeii and Herculaneum beneath volcanic deposits is one of the most extraordinary accidents of geological and archaeological history, and the scientific information preserved in those deposits continues to be extracted and studied nearly 2,000 years later. The eruption began on the morning of August 24th, possibly October 24th based on more recent evidence from preserved fruit and clothing found at the site, and produced a column of ash and pumice that rose to an estimated 33 kilometers, raining pumice down on Pompeii for approximately 18 hours and burying it under several meters of material. The city of Herculaneum, closer to the volcano, was engulfed by a series of pyroclastic surges, superheated mixtures of gas and volcanic material moving at hurricane speeds that killed the remaining population almost instantaneously. The heat of the pyroclastic surge at Herculaneum has been estimated at several hundred degrees Celsius, sufficient to vaporize soft tissue, and in some cases to cause the instantaneous boiling of brain matter, a finding made by researchers studying the skeletons of victims who had taken shelter in boat houses on the waterfront. The eruption preserved Pompeii in remarkable detail because a thick pumice layer protected the underlying surfaces from subsequent weathering, leaving behind painted walls, food still in cooking pots, the cast of human figures preserved in the exact postures of their death, and an extraordinary snapshot of Roman daily life in a prosperous provincial city frozen at a single moment in time. Vesuvius erupted into history and in doing so became one of the most important archaeological windows into the ancient world. Now settle a little deeper. Let the tension in your body release with each breath. We are going somewhere darker and more ancient now, somewhere very deep beneath the surface of the world. Lava tubes are tunnels formed by flowing lava, and they can extend for hundreds of kilometers underground, creating some of the most extraordinary cave systems on Earth. When lava flows from a volcano, the surface of the flow cools and solidifies first while the molten material continues to flow inside, insulated by the hardened crust above it. When the eruption ends or the flow source shifts, the remaining liquid lava drains out of the tube, leaving behind a hollow tunnel whose walls, floor, and ceiling preserve the textures and features of the solidified lava. Lava tubes on Earth can reach diameters of 15 meters or more and extend for extraordinary distances. The Tambora cave in Hawaii is the longest lava tube on Earth, extending for approximately 66 kilometers. The Undara lava tubes in Queensland, Australia, formed approximately 190,000 years ago and extend for over 100 kilometers, the longest known lava tube system in the world. Lava tubes are not simply geological curiosities. They are being studied as potential habitats for future human settlement on the Moon and Mars, where lava tubes have been identified by orbital mapping. A lunar lava tube would provide natural protection from cosmic radiation, micrometeorite impacts, and extreme temperature fluctuations, making it potentially one of the most suitable natural environments for long-term human habitation on another world. The volcanic feature that forms in the cooling margins of a lava flow on Earth may become the first home of human beings on another planet. The island of Iceland is one of the most volcanically active places on Earth and sits directly on the mid-Atlantic ridge, the diverging plate boundary where the North American and Eurasian plates are pulling apart. Iceland is one of the very few places on Earth where a mid-ocean ridge emerges above sea level, making it accessible for direct study. The island is entirely of volcanic origin, built from basaltic lava erupted over the past 16 to 18 million years as the plates have spread apart and fresh magma has welled up to fill the gap. New land is being created in Iceland right now, at the rate of approximately 2.5 centimeters per year as the plates continue to diverge. The Laki eruption in Iceland in 1783 and 1784 produced the largest basaltic lava flow in historic times, covering approximately 565 square kilometers with lava and releasing an estimated 120 megatons of sulfur dioxide into the atmosphere. The resulting haze, called the Laki haze or the dry fog, spread across Europe and produced one of the most severe winters on record, contributing to crop failures that some historians connect to condition preceding the French Revolution in 1789. Benjamin Franklin, observing the unusual cold and haze from Paris where he was serving as the American ambassador, was one of the first people to propose a connection between volcanic activity and climate change, making him perhaps the first person to identify this relationship in print. A volcanic eruption in Iceland contributed, through a chain of climatic and social effects, to one of the most consequential political events in modern history. The deepest volcanic activity on Earth occurs at the bottom of the ocean, and the lava it produces forms a landscape that covers approximately 70% of the Earth's surface. Submarine volcanism along the mid-ocean ridge system produces the oceanic crust, the dark, dense basaltic rock that forms the floor of all the world's oceans. At the ridge, tectonic plates pull apart and magma rises continuously to fill the gap, producing new crust at a rate of approximately 3 to 4 square kilometers per year globally. The lava erupted on the ocean floor behaves very differently from surface lava because of the enormous water pressure at depth. At the depths of the mid-ocean ridges, typically 2 to 4 kilometers below the surface, the pressure is high enough to suppress the boiling of water and suppress the explosive expansion of gas bubbles in the magma. Instead of erupting explosively, the lava oozes out of cracks in the seafloor and is rapidly chilled by the near-freezing seawater, forming rounded, pillow-shaped structures called pillow basalts that accumulate in layers on the ocean floor. Pillow basalts are among the most common rock types on Earth by volume, forming the foundation of most of the ocean floor, yet most people have never seen one because they lie kilometers beneath the surface of the sea. The entire Atlantic Ocean is floored with basaltic rock that has been produced by the mid-Atlantic ridge over the past 200 million years, and the rock that sits directly under the oldest part of the Atlantic, far from the ridge, was produced by submarine volcanism approximately 200 million years ago, when the Atlantic Ocean did not yet exist and the continents of North America and Europe were still joined. Let the room be completely still around you now. There is something very settling about the vast timescales we are moving through tonight. Your life is a brief, warm light in an immensity of geological time, and the rock beneath wherever you are resting was shaped by processes that began long before anything on Earth had eyes to see them. The pyroclastic flow is the most dangerous phenomenon associated with volcanic eruptions, and it is a feature responsible for the majority of volcanic fatalities in recorded history. A pyroclastic flow is a fast-moving current of hot gas, ash, and volcanic fragments that flows down the flanks of a volcano after the eruption column becomes too dense and heavy to remain buoyant in the atmosphere and collapses. The resulting flow moves at speeds that can exceed 700 kilometers per hour and carries material at temperatures between 300 and 800 degrees Celsius. Nothing in its path can survive. Buildings are demolished by the pressure wave ahead of the flow before the heat arrives. Vegetation is stripped from slopes and incinerated. The air itself, superheated and laden with fine ash, is not breathable. Pyroclastic flows can travel for tens of kilometers from the volcano at speeds that outrun any vehicle on an unpaved road. The eruption of Mount Pelée on the Caribbean island of Martinique in 1902 produced a pyroclastic flow that destroyed the town of Saint-Pierre, at the time the largest city in the French Caribbean, in approximately 2 minutes. Of the approximately 30,000 people in the city, 3 people survived, one of them a prisoner in a thick-walled cell that provided just enough insulation from the heat. The rapidity of the destruction and the near-total loss of life at St. Pierre made it the deadliest volcanic disaster of the 20th century and changed the scientific understanding of the range of phenomena that volcanic eruptions could produce. Volcanoes are not only agents of destruction. Over geological timescales, they are the primary builders of the world as it exists. The atmosphere you are breathing right now was produced largely by volcanic outgassing over the past 4.5 billion years. The early Earth had no significant atmosphere. As volcanoes erupted continuously throughout the Hadean and Archean eons, they released water vapor, carbon dioxide, nitrogen, sulfur dioxide, and other gases from the interior of the planet in a process called outgassing. The water vapor condensed as the surface cooled, filling the first oceans. The carbon dioxide was gradually drawn down from the atmosphere by weathering reactions and by the first photosynthetic organisms, replacing the atmosphere by the oxygen those organisms produced. The nitrogen remained, accumulating over billions of years to become the dominant component of the atmosphere it is today. Without volcanic outgassing, the Earth would have no atmosphere, no oceans, and no life. Every breath you take contains nitrogen that was released from the interior of the Earth by volcanic activity over billions of years. The air itself is, in the deepest sense, a product of volcanism. Volcanic soils are among the most fertile on Earth, and the reason that hundreds of millions of people live on the flanks of active volcanoes despite the obvious danger is that the agricultural land those volcanoes have produced is extraordinarily productive. Volcanic soils, called endosols, are formed from the weathering of volcanic ash and lava, and they are unusually rich in minerals, particularly phosphorus, calcium, potassium, and magnesium, that are essential for plant growth. The volcanic ash that blankets the surrounding landscape after an eruption weathers relatively quickly compared to other rock types, releasing its mineral content into the soil over decades and centuries. The slopes of Vesuvius in southern Italy, Mount Etna in Sicily, the Pinatubo region in the Philippines, and the flanks of the many volcanoes of Java and Bali support some of the most intensively farmed and densely populated agricultural landscapes in the world. The people who farm these soils know the risk they are accepting, and many have farmed the same volcanic slopes for generations, accepting the periodic catastrophic reset as a price of the extraordinary productivity that the volcano provides between its episodes of destruction. The volcanic island of Java, covering less than 7% of Indonesia's land area, supports approximately 60% of its population, a density made possible in large part by the fertility of its volcanic soils. The same force that destroys with fire rebuilds with minerals, and the cycle of destruction and renewal that characterizes volcanic landscapes has been the foundation of human agriculture in many of the most densely populated regions on Earth for thousands of years. There are volcanoes on other worlds, and the most volcanically active body in the solar system is not Earth but Io, one of Jupiter's moons. Io is kept in a perpetual state of volcanic activity by the gravitational tidal forces exerted on it by Jupiter and the other large moons. As Io moves in its orbit, the gravitational pull from Jupiter stretches and compresses it, generating heat through friction in the interior in a process called tidal heating. The result is a surface so volcanically active that it is constantly being resurfaced, with craters erased almost as quickly as they form. Io's volcanoes include some of the most powerful in the solar system, erupting with lava that is thought to be significantly hotter than any lava erupting on Earth today, possibly comparable in temperature to the lavas that erupted on the early Earth billions of years ago when the interior was hotter. The Voyager spacecraft, passing Io in 1979, captured the first images of active volcanic eruptions on another world, with plumes of sulfur dioxide rising hundreds of kilometers above the surface. The sight of those plumes in the Voyager images was one of the most unexpected and dramatic discoveries of the space age. A small moon of Jupiter, overlooked by all expectations, turned out to be the most volcanically active object ever discovered by human instruments, a world of constant fire fed not by radioactive decay or residual primordial heat, but by the gravitational embrace of the largest planet in the solar system. The concept of the supervolcano, a volcano capable of producing an eruption of truly catastrophic scale, has entered popular culture largely as a subject of disaster narratives, but the geological reality is both more nuanced and more fascinating than any fictional account. A supervolcanic eruption is defined as one that produces at least 1,000 cubic kilometers of eruptive material, a threshold that places such events in a category of geological violence that has no equivalent in recorded human history. The Tambora eruption in Sumatra approximately 74,000 years ago is the largest known supervolcanic event in the last 2 million years, ejecting approximately 2,800 cubic kilometers of material. Genetic evidence suggests that human populations may have been dramatically reduced in the aftermath of the Tambora eruption, possibly to a few thousand individuals, as the volcanic winter produced by the eruption caused widespread crop failures in a world where humans were entirely dependent on wild food sources. This population bottleneck hypothesis is debated, but the climatic effect of the Tambora eruption was certainly severe and global. The caldera left by the Tambora eruption is now occupied by Lake Toba, a lake approximately 100 by 30 kilometers, the largest volcanic lake in the world. Sitting in a boat on the tranquil blue surface of Lake Toba, looking at the forested hills rising from its shores, it is almost impossible to connect that peaceful scene with a geological event that shaped human population genetics 74,000 years before the first person looked at that water. Now let the weight of the world, both its geological weight and the weight of your own day, release completely. The volcanoes will continue their work tonight without any help from you. The convection currents will keep moving in the mantle. The plates will keep drifting. The lava will keep flowing at the ridge. Everything that needs to happen is happening, and none of it requires you to stay awake. Some volcanoes have been continuously active for so long that human civilization cannot remember a time when they were quiet. Stromboli, a small island volcano in the Tyrrhenian Sea north of Sicily, has been erupting almost continuously for at least 2,000 years and possibly much longer. Its mild, regular explosions of incandescent lava fragments and gas, occurring every 15 to 20 minutes on average, have been observed by sailors for millennia and gave Stromboli the ancient name the lighthouse of the Mediterranean. The regularity and relative mildness of Stromboli's activity makes it one of the most studied volcanoes in the world and a destination for volcanologists who wish to observe active eruption processes at close range over extended periods. Eruption in Ethiopia is a shield volcano in the Afar Depression that has maintained a persistent lava lake in its summit crater, one of only a handful of permanent lava lakes on Earth, for as long as recorded observation extends, at least since the early 20th century and possibly much longer. The surface of the lava lake is a thin crust of solidified rock over convecting molten basalt, and the crust constantly fractures and overturns, exposing the glowing liquid rock beneath in patterns that shift and reform over minutes. Sitting at the edge of Eruption at night and watching the surface of the lake breathing and folding in the darkness below is described by everyone who has experienced it as one of the most profound and primal encounters with the living earth that any landscape on the planet can offer. The volcano is not simply geological. It is elemental. It is a planet thinking out loud in fire. The study of volcanoes has driven some of the most important advances in earth science, and the data collected from monitoring active volcanic systems continues to produce discoveries with consequences far beyond volcanology itself. The monitoring of the deformation of volcanic flanks using GPS, satellite-based radar interferometry, and tilt meters has produced techniques that are now also used to monitor the slow movement of landslides, the subsidence of cities built on soft sediments, and the deformation of the crust associated with earthquake fault zones. The analysis of gases emitted from volcanoes, particularly sulfur dioxide and carbon dioxide, has provided insights into the deep carbon cycle and the processes that regulate the long-term carbon content of the atmosphere. The study of volcanic deposits in ice cores, identifying the chemical signature of past eruptions preserved in the ice record, has allowed researchers to build a timeline of major volcanic events over the past 800,000 years, and to connect those events to the climate fluctuations recorded in the same ice cores. The geophysical monitoring networks built to track volcanic activity have provided dense arrays of seismometers and other instruments that also contribute to our understanding of the structure of the Earth's interior, the behavior of the mantle, and the mechanics of tectonic plate movement. Volcanology began as a study of a single spectacular phenomenon and became, through the accumulation of data and the development of monitoring technology, one of the most productive windows into the deep workings of the entire planet. The night is very deep now, and you have come a long way from the surface of the world. Let the last of the wakefulness dissolve. Let the darkness be complete and comfortable. The molten rock is moving somewhere far below, doing what it has always done, and the surface is still and cool and quiet, exactly where you are lying. Volcanic islands are among the most remarkable examples of life colonizing new territory, and the process by which a bare, sterile volcanic island becomes a complex, biodiverse ecosystem is one of the most vivid demonstrations of ecological succession in the natural world. When a new volcanic island rises from the ocean, its surface is bare rock, with no soil, no nutrients, and no life. The first colonizers are typically microorganisms, bacteria, and algae that can survive on bare rock and begin the slow process of weathering its surface and building the first thin films of organic material. Lichens follow, their acid secretion continuing to break down the rock while their bodies add more organic material to the developing protozoal. Moss is established in the thin layer that the lichens prepare. And ferns, whose lightweight spores can travel thousands of kilometers on the wind, are typically among the first vascular plants to establish on new volcanic islands. As the soil deepens and the first plant provide habitat and food for insects and birds, the island gradually accumulates species, each new arrival opening opportunities for more. The Hawaiian Islands, which arose from the same hotspot now building the Big Island, show this process at different stages, with the oldest island supporting the most complex and specialized communities and the youngest showing the earliest stages of colonization. The bare lava fields of a recent eruption, black and sterile and apparently lifeless, contain within the beginning of a forest that will develop over thousands of years in a process set in motion by the same volcanic activity that created the ground it grows on. And so we drift gently back from the world of volcanoes, carried upward through the layers of rock to the still surface of the night, carrying with us a quiet weight of everything we have visited. We stood at the edge of the ring of fire and traced 75% of the world's volcanic activity to the geometry of one ocean's boundaries. We watched Tambora cool the entire planet for a year and feed a chain of consequences that reached from crop failures in New England to revolution in Paris. We descended into lava tubes that may one day become the first homes of human beings on another world, and found the pillow basalts of the ocean floor recording 200 million years of history beneath every ocean on Earth. We watched pyroclastic flows move faster than any vehicle can escape, and felt the ancient fertility of volcanic soils that have fed civilizations for thousands of years despite their proximity to destruction. We visited Io and found the most volcanically active body in the solar system burning not from radioactive heat, but from the gravitational embrace of Jupiter. We sat at the edge of Ota Ale and watched the surface of a permanent lava lake breathe and fold in the darkness, the planet's interior visible from the outside at a place where the surface is thin enough to see through. The volcano is the Earth speaking in its oldest language, the language it has been speaking since before there was a surface to erupt onto, and it has not stopped speaking in 4.5 billion years. Tonight, for a little while, you listened. If you enjoyed this sleepy journey, you could support the channel by liking, subscribing, or leaving a calm little comment before you rest. It helps more curious minds find their way here. And if you are still awake, there's another video waiting on your screen, ready to carry you onward into another corner of science. But for now, let the questions loosen their grip. Let your shoulders soften. Let your jaw unclench. Allow your breathing to slow, steady, and deepen. Picture the ground beneath wherever you are, dark and solid and ancient, and somewhere far below it, so far that no drill has ever reached, the slow movement of rock that is not quite rock anymore, not quite liquid, moving in currents measured in millions of years, carrying the heat of the planet upward in the endless, patient process that has been keeping this world alive since the beginning. You are resting on the surface of something ancient and alive, held by it, warmed by it, sustained by the same interior fire that lights the volcanoes and builds the islands and breathes the atmosphere into being. You do not need to understand it all tonight. You only need rest. Sleep well, and good night.